Okay. Welcome back, everyone. So today we are gonna start chapter 3. The first thing I would like to do is just again to summarize very quickly chapter 2. And I'll try to do that through questions. So I will ask you questions and you can try to see if you have the right answer, at least in your mind, and hopefully if you can spell it out, that would be also very nice. So the first thing that we learned in chapter 2 is what OLS does. What is OLS doing? Does somebody remember? Yes, it minimizes the sum of square. And why does it minimize the sum of square? What is it estimating? Yes? Exactly. So the best fitting line to predict a variable y from a variable x. Here the hours and rate. Okay? And this line is a prediction device. It's a way to predict the y variable linearly from the x variable. If you apply OLS, let's say, to predict wages linearly from education, do you get the same result if you apply OLS on all the population of Belgium or on a sample of 1,000 of Belgians? No, you don't, right? So in a way, you can say that in practice there is some kind of true line. The true best line is the one that you would get if you run OLS on the full population of interest. So let's say the full population of Belgians. But in practice, in statistics, you only have a small sample. You almost never observe a full population. And in that case, you're gonna, if you run OLS on a sample of 1,000 Belgians, regressing wages on education, then you're gonna get an estimate of this line that you would have if you had run OLS on all the population. Now, what we also learned is you can formalize this line through this linear model. You can always show that there exists a b, which corresponds to the slope of the line, such that the variable yi is equal to xi prime b plus some error term that is uncorrelated with xi. So this b is just the baseline, under which assumption is this baseline a causal quantity. When can we interpret this baseline under as a causal effect? Yes? That's one, yes, and linearity. So essentially what you need to interpret B, which as I said always exists, B is the best way to predict linearly y from x. If you want to interpret this as causal, you need the true causal model to be this one. So the true model that really generates the data causally. This is not a correlation, that's a causation model. And if the true model is this one, that means two things. The first one is exogeneity, as you said. So xi is not correlated with the error term. That's a strong assumption, because if you think of yi being wages, xi being education, if ui is, say, intrinsic ability, exogeneity will mean that intrinsic ability is not correlated with education, which seems to be a very strong assumption. The second assumption is linearity. Here you see that the effect of x on y is linear in x. Meaning, say, the effect on wages of going from 0 to 1 year of education is the same as going from 1 to 2, from 2 to 3, and it goes on. So that's also a strong assumption. Now, for simple linear model, it's not very credible to think that the linear model is a causal model, right? Because you need this exogeneity assumption and these linearity assumptions. But last time we saw that there was maybe a way to make linear models more likely to be the causal model, a way to make these two assumptions more realistic. And what was this solution? You can add more variables. So if you add more variables, first, if you add more variable in X, in a way, you are taking things out of U. So if you add a variable like IQ in X, you're taking a part of ability out of U, and you make it more likely that the part of ability that is not correlated with IQ will be uncorrelated with education. So you make the exogeneity more likely. The other thing is that you can also add more variable in the way that you add interaction or transformation of your original variable. If you add education to the square, then the effect is not linear in education anymore, and you make the model more realistic. So we saw that adding more variables can make the model more credible for causal inference. Another thing for which it's useful is to improve predictions, right? So when you think about it, the current model, like the simple model, is just predicting from a few variables. It's logical that if you add more variables, your linear prediction should become better. So it can improve predictions, but there is a caveat, of course. So essentially, last time we discussed what OLS is doing. OLS is estimating this best fitting line. And we said it's often nicer to estimate linear models with more variables, because that makes the best fitting line more likely to be interpretable as a causal effect, but also it can improve the predictions. But what we also saw last time is that OLS was doing very poorly in high-dimensional datasets. So high-dimensional datasets are datasets where you have many variables with respect to the sample size. And this is what arises when you add many variables to your linear model. In particular, what we saw through simulation is that when you increase the number of variables, while the bias of OLS was always staying 0, theoretically the variance of OLS was exploding. And what was happening here is this phenomenon called overfitting. And the idea of overfitting is just to say that when your model is too flexible, when you're going to estimate on your data, you're not only going to reproduce the B part, so the structural part, you're also going to reproduce the error term. And that's what you don't want to reproduce, because the error term is not the structure of the data, it's something observation specific, right? So you want to reproduce a structure, but not something that is specific to every observation. So I think I always like, and I'm sorry I don't have white chalks today, but I think I always like this kind of graph to see. So suppose that you try to predict y from x, for instance, and this is the true model. Okay, so this is in a way the best prediction from y from x. And then you have some error terms. So you have some data points, and these data points are like that. They follow this curve, but with some errors that makes it going away from the curve. So that's basically what happens in real life. Now, if you have a model that is too flexible, rather than recovering the curve, it's going to do something like that. It's just going to pass by every point. And when this happens, you see that this is very bad. This yellow line here is very far away from the blue line. So your predictions become very bad. And the reason why it becomes very bad is because you say, in a sense, since I fit all my points, if I see something with that x, I'm going to say it is going to have this y. But that's a very bad prediction. The true one is this one. Okay, and that's because we really only reproduce the error terms. So this is just an error term. Is this clear for everyone up to now? So what we also saw last time is a solution to the problems that OLS faces and of overfitting. And this solution is to use lasso. So the idea of lasso is essentially we are going to restrict the flexibility of the model by somehow imposing that the lines for which we are looking for are sparse. By sparse, that means they only have a few non-zero coefficients. So the way to interpret that is that only a few variables in X are important to predict Y linearly from X. We don't know which ones, but we are assuming that there are only a few. And Lasso is just an estimator with a complex computational machinery that I will not go through over today again, that ensures this. And when you reduce this model flexibility in that way, you avoid the overfitting. That's what we saw last time. What happens with the lasso? So you run your lasso, there is some lambda penalty term that determines how sparse the lasso will be. We can choose it through cross-validation, that's what we saw last time. And then what we also saw in simulation is that essentially the nice thing with that is that the bias stays under control, and mostly the variance stays under control. So this lasso is solving this overfitting issue. So in a sense, we have solved the problem that OLS doesn't work when in high-dimensional data by saying, okay, rather than looking for any possible line, because if we look for any possible lines, then we are bound to overfit, we are too flexible, we are going to look for sparse lines, and that's what Lasso is doing. And so last week, we had this tutorial. And in the tutorial, you saw a striking example of overfitting. So if you remember, we tried to predict the price of flats as a function of several variables. You had the number of square meters when the flat was built and the number of rooms. If we have a simple linear model with just these three variables linearly, we saw that Lasso and OLS were doing exactly, essentially the same job at prediction. Now, when we increase the number of variables by including powers of these original variables on interactions, what happened? We saw that OLS was doing a very good job in sample. So if we were trying to see if OLS was making good prediction on the sample on which it was estimated, it was doing very well. So essentially, it was doing something like that. It was fitting perfectly the sample points. Okay? But when we were trying to apply OLS to a new sample, to new data, it was doing extremely bad. And that's because of overfitting, because OLS has been reproducing the noise of the sample on which it was trained. But by reproducing this noise, it cannot predict well on new samples, because the noise is different on new sample. What is the same thing on the new sample is the beep, but not the noise. So you don't want to reproduce the noise. And contrarily, Lasso was doing very well. Okay, is that clear for everyone? Okay, so if you have understood all these ideas, you've understood an important share of the concepts of the course. So now we can go to chapter 3. So what is the link between chapter 2 and chapter 3? Essentially, in chapter 3, we have mostly talked about prediction still, right? Like, when you look at the tutorial, I have shown you that OLS does very badly at prediction when it overfits. But often we are not, in causal inference, we are not interested in the prediction, we are interested in the causal effect. So we are interested in this best fitting line under the assumption that you can interpret it as a causal effect. So now we are going to discuss what happens with Lasso when you are interested in B. That's what we are going to do in this chapter. And what's important is it's actually quite complex to do hypothesis testing on B with the Lasso, while for OLS it's very simple. You have seen OLS, you have an asymptotic variance, you construct a confidence interval or a test. For Lasso it's a bit more complex, and that's what we are going to see in this chapter. So the name of the title of the chapter is Inference with the Lasso, and what we mean here by inference is hypothesis testing, essentially. So how can we evaluate if a result is very uncertain or not? So let's go through it. So the first thing is I want to give you a reminder on inference with the Lasso and with OLS, sorry, and hypothesis testing with OLS. So let's fix the problem. So I want to learn the causal effect of education on earnings. Always my same example. And I'm going to suppose, for now, that the causal model is linear, and this is this model. Of course, you might tell me this is not realistic, but this is a toy example to understand what's happening. So I suppose that earnings is linear in education and experience, plus some error term, which is uncorrelated with education and experience. Okay, so this is, I suppose that this model is a causal model. So I can estimate it by OLS. Here, beta 1 is the causal effect of education ceteris paribus. So again, this makes very strong assumption. That means that the effect of education is linear, that there is exogeneity. But let's maintain this assumption for now to understand what's happening with OLS and what will happen with lasso. So the main question you might have is beta 1 different from 0? Has education a causal effect on earnings? So to answer this question, we collect data on a subsample of the Belgian population. So let's say beta 1 is a causal effect of education in Belgium. To answer the question, I'm going to collect data on 1,000 Belgians. I run the regression, and I get beta 1 hat, which is the OLS estimator. Of course, beta 1 hat is not beta 1. Beta 1 will be what you get if you run the regression on all the Belgian population. Here you only observe 1,000 Belgians. So beta 1 hat is not exactly beta 1, right? It's the same if you want to estimate the average wage in Belgium, you're not going to get the same result if you just average over 1,000 Belgians randomly selected and all the Belgians. Now the main question is statistical uncertainty. If I find, for instance, beta 1 hat is equal to 0.2, does that mean that I can confidently conclude that the true beta 1 is non-zero? And this is something that depends from the statistical uncertainty of the problem, the sample size, and a lot of things. So essentially what I want to do is hypothesis testing, statistical hypothesis testing. So I want to test the null hypothesis H0 beta 1 is equal to 0 against the alternative hypothesis beta 1 is different from 0. So how do we do hypothesis testing in econometrics or in statistics? It's quite similar to what's happening in the justice system. I always use this metaphor. So, and in the justice system, you have this presumption of innocence. Let's say you want to know if person A killed person B. You're going to start from the assumption that person A is innocent, that they did not kill person B. Under this assumption, you're going to have some kind of distribution of possible facts in your mind. If person A did not kill person B, then it's very likely that they were at work on the day of the murder at the time of the murder, or that they were at home on the day of the murder at the time of the murder. If you observe something that is very unlikely under this hypothesis of innocence, say somebody saw them just next to the murder place almost at the time of the murder, then you can reject innocence. If you observe something which is completely coherent with innocence, you don't reject innocence. So what's happening essentially in the justice system is we start from the null hypothesis. We think what is the normal thing that we should observe under this null hypothesis. If we observe something that is very unlikely under the null hypothesis, say, as I said, the suspect was seen close to the murder place at the time of the murder place, then we can reject this null hypothesis of innocence. So that's what's happening in the justice system, and that's essentially what we do also in statistics. So we start from the null hypothesis. We assume that this is true. When this is true, we can know what is the distribution of OLS. Because we have this result from the central limit theorem. So this result is telling us that square root of n beta hat minus beta converges to a normal 0 sigma. What does that mean? That means beta is my true coefficient of interest. That's the one I will get if I estimate, I run OLS on the full population of Belgians. Now, in practice, I don't observe the full population of Belgians, so I just draw a sample of 1,000 Belgians. There are infinitely many such samples that I can draw. Each of these samples will give me a beta hat. If I look at the distribution of samples of beta hat across all these samples of 1,000 Belgians, then what I can show mathematically is square root of n times beta hat minus beta will converge to a normal distribution. So what does that mean? If I consider all the possible samples of 1,000 Belgians, on each of them I compute beta hat, then I compute square root of n beta hat minus the true beta, then this looks increasingly normal as I increase the sample size. Another way to write this, which is not fully rigorous, is essentially to say that beta hat is gonna have a distribution that is a normal with mean beta and variance sigma over n, right? I just put the beta on the right-hand side and I divide it by square root of n. So if I assume H0 beta is equal to 0, then this implies that beta hat follows approximately a normal 0 sigma over n. So under H, what I know is that under H naught, under the null hypothesis, if I look at, if this null hypothesis was true, if I look at the beta hat across all the possible samples of 1,000 Belgians, then the distribution of those beta hats should be a normal 0 sigma over n. Now, this, for instance, this is, let's say this is a normal 0 sigma over n. That means that if you draw one point from this distribution, this gives you the probability mass that it is at different points. So that means that if H0 is correct, it's much more likely that H0 is in this area, that the beta hat is in this area, than that it is here or here. That clear for everyone? Or should I repeat? Under the null hypothesis, the distribution of the beta hat across all samples of 1,000 Belgians will be this one, if the null hypothesis is correct. In practice, I only observe one beta hat. But what I can check is this beta hat that I observe likely or not under this distribution? If my beta hat in my sample is here, it's likely under this distribution. Okay, there is no problem. In a sense, the facts that I observe in practice are coherent with the assumption of H0 or the assumption of innocence. They are not something that I should expect not to observe if the person was innocent. Now, if my beta hat that I observe in my sample is here, what does that mean? That's very unlikely to happen under the null hypothesis, because if the null hypothesis is correct, this should be the distribution of the beta hats. So it's very unlikely that I find a beta hat that is here. So this case of beta hat is kind of the case somebody saw person A close to the murder place at the time of the murder. That's something that could happen under innocence, but is very unlikely. So essentially what I'm doing in practice, what we will be doing with hypothesis testing is that we are going to look at this distribution. If we find a beta hat that is very unlikely under this distribution, if my beta hat is very unlikely under this distribution, I'm going to reject H0 because I will have something that seems extremely unlikely if H0 was true. Now, if I find in my sample my beta hat is here, then I'm not going to reject H0 because what I see in my sample is completely coherent with the null hypothesis. Okay, so this is a case where the person was seen at work around the time of the murder. So this is completely coherent with innocence. I don't reject innocence. This is a case where the person was seen close to the murder place at the time of the around the time of the murder, so I reject innocence. Is this clear to everyone, or should I repeat? If you have any question, please don't hesitate. This kind of thinking is a bit counterintuitive sometimes, so it's normal if you struggle with it, but the goal is to make sure you understand it. So again, this is the distribution of beta hat. This is a distribution of standardized beta hat. So what we call standardized is just beta hat divided by the variance. This is what you should expect. And this is what I was telling here. So if this is the distribution that you should expect of beta hat, and this is your beta hat, you see that you are on the side. When you are unlikely enough, so what's happening is that you're going to have what we call a p-value. So the p-value here, the p-value of a test is just the probability that you find a beta hat which is larger in absolute value than this if H0 was true. So to measure the degree of confidence in H0, we use the p-value. So the p-value is just the probability under the null hypothesis that you would observe a beta hat that is larger in absolute value than the beta hat in your sample. So if this is the beta hat in your sample, this is, let's say, these zones here, this is badly drawn, these zones are just the zones where beta is larger than the beta hat in absolute value, and I look at the probability of these zones. The more the beta hat I observe in my sample is unlikely under the null hypothesis, the more the probability of these zones is small under the null hypothesis. Okay? So the p-value is just the probability of this area. So the smaller the p-value, the less likely H naught is. Okay? Is that clear for everyone? So if my beta hat was here, and here this is my minus beta hat, then the probability to observe a beta hat which is larger than the one I have in my sample will be all of the probability of observing something here and the probability of observing something here. So the p-value will be very small. Will be very large. Now, when beta hat is on the tail, the p-value is much smaller, and you're much more likely to reject H0. Is this clear for everyone or not? The p-value, because people confuse all the time. Is that clear? Okay, good. So that's the way the test works with OLS. What you also see here on this graph is interesting. So suppose the alternative hypothesis is true, then what you see here is that beta hat is still going to follow a normal, but this normal will be translated by the true beta. So when the true beta is large, beta hat will follow a normal with a very large mean, for instance. So the true beta hat, the distribution of beta hat will not be this normal centered at 0 anymore, but for instance, this normal which is to the side of 0. So what happens in that case? Well, you're very likely to find a beta hat that is unlikely under this normal, right? Because you have a normal to the right of it. Your beta hat in your sample is going to be generated by this normal, so you're very unlikely to find this normal, to find something that is likely under the normal above. So that's why you're gonna reject. Okay. So now let's move to inference with OLS, with the lasso. So with OLS, we said, how do we do inference? We use asymptotic normality of OLS. For OLS, we know under H0 what should be the asymptotic distribution of beta hat. So we know what is the distribution of the facts we should observe, and we can use this to construct a test. If what we observe is unlikely to happen under the distribution that we should of facts that we should observe under H0, then we can reject the null hypothesis. With lasso, things are more complex. And that's because, unlike OLS, the lasso is not asymptotically normal. The lasso, all this construction relied on asymptotic normality, it relied on this. This is true for OLS, but this is not true for the lasso. And this is because the lasso introduces bias that OLS doesn't have. Here you see that since square root of n beta hat minus beta follows a normal distribution centered in 0, you see that on average, beta hat is equal to beta. There is no bias. For OLS, that's what we discussed. That's not the case with lasso. Lasso has bias, and that's what we saw in the simulation in chapter 2. Lasso is introducing some bias to contain the variance. So if you use the standard lasso estimator, then this lasso estimator will not be asymptotically normal, and you can't do this construction of the test. So what we need to do inference with the lasso is to change the construction, to use a different construction that will use lasso at some step, but that will allow us to do inference using lasso. So in a different, another way to put that is that we are going to use lasso to construct methods to do inference when we have high-dimensional data. But these methods are more complex than just lasso. When your data is low-dimensional, you can just use OLS, you have no problem. When your data is high-dimensional, you need one of these two methods that we will see, double selection or double machine learning, to do inference. These two methods rely on lasso, but they are not exactly lasso. So lasso itself is not enough to do inference in this setting. So we will see these two methods. What you should know is that these two methods, they are asymptotically equivalent, meaning when the sample size goes to infinity, their results converge to each other. So there is no really method to prefer to one another. They will give you very close results in practice, but we see both methods because they both have different interpretations, which are interesting for understanding. So let's formalize the problem. So we are again trying to do inference, so hypothesis testing, and this is the way I'm going to write the model. So I'm going to say yi is equal to alpha di plus xi transpose beta plus epsilon I. And my interest is in the coefficient of di, so the alpha. I want to do hypothesis testing on this alpha. So think of this as yi could be wages, di could be education, and then x is a bunch of controls. So in this bunch of control, I'm going to have parental education, IQ, where you were born, your experience. In the US, they have sometimes ethnicity and religion and these kind of things. So think of this as I want to do inference on alpha. I have a linear model with many controls in my X. And the difficulty here is really that xi is high dimensional. If xi was low dimensional, I can just run OLS. I saw that earlier, no problem. Now xi is high dimensional, I have many controls. I can have transformation of these controls, etc. And we want to test alpha is equal to 0. Here I give you a second example. So the first example was education. It's also, a second example is a gender wage gap. So suppose you want to estimate the gender wage gap. So you want to know what is the wage difference between women and men who have the same observable qualities except gender. So you will see in the literature a lot of these estimates of gender wage gap, where you see that women with the same observables are paid much less than men. So we want to do that, and to do so, our yi will be the log of hourly wage. Di will be gender. As I said, it's all data. This is a CPS 2012 data, so gender is just a binary variable here in this all data. And xi is going to be occupation, full-time work, age, ethnicity, marital status, and a lot of controls. Okay, so that's a case where you want to estimate the effect of gender on wages once you have control for all of these other things. And of course, if you just run yi on di as a regression, you run into an endogeneity problem, because it could be that women have different occupation preferences, and that's the reason why they are paid less, not because there is any discrimination. So you want to, if you want to isolate the discrimination effect, you need to put a lot of control. Particular education, age, ethnicity, if they work full-time, and these kind of things. So this is an idea of a problem. So one very naive approach here to do inference with lasso would be, I first run lasso in this regression. So this is my lasso. And then you remember the lasso gives you a sparse solution. So it gives you an estimators alpha at L, beta at L, which are sparse, meaning that most variables in the estimate have a 0 coefficient. So I run this lasso. You will actually notice that I don't penalize the coefficient of D here to make sure I always select it. But I run this lasso. This lasso will give me some coefficient. And as we saw in the tutorial, most of them are going to be 0. So let's say in my beta, I will see that occupation doesn't have a 0 coefficient, but maybe all the other variables will have 1. Then I can say, in a sense, I just select these variables that lasso gives, to which lasso gives a non-zero coefficient in X, and then I just run OLS of the regression of yi on di plus the variables to which lasso gave a non-zero coefficient. Okay? And then I could hope that this would work, because I know OLS is asymptotically normal. So that's a naive way to look at the problem. I first use lasso to select the variables. Lasso gives me a sparse solution, so it gives me only a few variables with a non-zero coefficient. I take these variables and then I run OLS, because I'm back to a low-dimensional problem, right? Lasso has selected a few variables, so it's low-dimensional, this last step regression. But it turns out, so these are simulations. It turns out, coming from this paper, the reference is on slide 48, and it turns out that this estimator, so that we call post-lasso, so we first do lasso, then we do OLS, so it's called post-lasso, is not asymptotically normal. In red here, you have the distribution you would expect the estimator to have if it was asymptotically normal. And in blue, this is the distribution it has in simulations. So you see that this estimator is not asymptotically normal. I will try to explain to you why. But that's what's happening here. So what's happening? There is something that we call omitted variable bias, that I'm sure you have all heard about. So suppose I want to estimate B1 in this model. So say yi is wages, x1i is gender, and x2i is occupation. So that's my example of before. When will the regression of yi on x1i only give me something that is biased for B1? This will happen if two conditions are met at the same time. The first condition is B2 is non-zero. The second condition is x1i and x2i, sorry, are correlated. So think of this on the following way. What happens if, let's say, this is a true causal model, but I run a regression without x2i? Then what the regression without x2i is doing, essentially, is comparing the wages of men and the wages of women, and just looking at the difference, right? This will not be a causal effect if two conditions are met. The first one is you need the occupation of men and women to be different on average. Okay, so that's this correlation between x1i and x2i. The occupation of men and women are different on average. And second, the occupation has an effect on wages. If these two things are true, then when you just compare the wages of men and of women, then you're not identifying the causal effect of being a woman. You're just identifying a mix of the causal effect of the fact that women and men have different occupation and gender discrimination. And this issue only happens when occupation is correlated with gender, and at the same time occupation has an effect on your wages. If occupation had no effect on your wages, then you can safely ignore it, right? That doesn't change anything. Even if women and men have different occupations, that doesn't matter for the estimation of the causal effect. If occupation has an effect on wages, but women and men have have the same occupations on average, then you can also ignore it. But you can't ignore it if both occupation matters for wages and the women and men have different occupation. So what this is telling you here is when you select variable, when you put variables in a regression, you want to avoid omitting variables that both have an effect on your outcome and are correlated with the variable of interest, here gender. When you omit such variables, that's called omitted variable bias, it creates a bias in your estimation. So why is this problem happening? So Lasso is a prediction device. So it's going to select some variable in X. But it's going to select this variable in X just on the basis that these variables have a prediction effect on Y. So in a sense, it's going to look for variables which have this beta 2 non-zero. which have a predictive effect on x, on y, sorry, but not for variables which have this. So what will happen in practice is that there will be some variables that have an effect on y, but this effect is very small, but are very correlated with gender. And this variable will often be missed by lasso. And they are missed by this lasso because they have a very small effect on y. So for lasso, it's very hard to see that these variables matter, but they will still create a lot of omitted variable bias because they are very correlated with gender. In particular, what I tell you here is that if you have a variable in xi that is very correlated with di, typically it will help you very little for prediction, so it's very unlikely to be selected by the lasso, but at the same time it can create a lot of omitted variable bias because it's very correlated. So essentially what the post-lasso is doing is the problem is that it misses variables which have a very small B2 but a very large correlation with gender. And when you miss these variables, then you create this omitted variable bias. Okay, so the solution is, one solution is as follows, it's double selection. So we are going to do a different type of selection. What I told you here is the problem is if I do post-lasso, there will be some variables that I'm not going to select because I have a very small B2, in a sense, but I still create a lot of omitted variable bias because they are very correlated with gender. So what I want to do is also add in my last step regression the variables which are very correlated with gender, essentially, because then I solve this problem. So what double selection is doing is the following. First, I'm going to run the lasso regression of di on xi. And this lasso regression will give me a set of variables that have a non-zero coefficient that I can select. So this lasso regression is going to select variables which are very correlated with di. So it's going to select variables that satisfy the second condition. Then I'm going to run another lasso regression of yi on xi. When I run this lasso regression of yi on xi, I'm selecting the variables that have an effect on yi. So I'm selecting the variables that satisfy the first condition. And then at the last step, I run OLS for the regression of yi on di, using as control the covariates that are selected by by either of the two steps before. So in a sense, the first step gives me a set of variables. The second step gives me a set of selected variables. I take the union, and I use that for OLS in the last step. And what is essentially happening, I think I say it here, the first lasso regression is going to pick all regressors that are very correlated with di. It might miss some regressors which are not very correlated with di, but it's going to pick all regressors very correlated with di. The second lasso regression is going to pick all regressors that are very correlated with yi. It might miss some that are not very correlated with yi, but all the ones that are very correlated with yi will be captured by this regression. So together, the two lasso regression, they are going to select all variables which are either very correlated with yi or very correlated with di. So the variables that are not selected in double selection are variables that have to be, at the same time, not very correlated with di and not very correlated with yi. So in other words, they create very little omitted variable bias. You remember what creates omitted variable bias is being correlated with yi and being correlated with di. The variables that are not selected by these two steps, They are just the variables that will create very little omitted variable bias, because not to be selected by the first step, you need to be very little correlated with DI, and not to be selected by the second step, you need to be very little correlated with YI. So the variables not selected by the two-step are both very little correlated with YI and with DI, so they are not going to create a lot of omitted variable bias. And that's why these two steps together kind of avoid this selection problem. They essentially together select all variables that might create a lot of omitted variable bias and cause this asymptotic normality to fail. And what you see in simulation here is, so this was the post-lasso that we saw before, and this is a double selection. So the double selection works because it has essentially selected all the variables that can create substantial omitted variable bias. The post-lasso doesn't work because among the variables that can create substantial omitted variable bias, it has forgotten the one which are not very correlated with YI, but are very correlated with DI. Is that somewhat clear for everyone? I will explain it again after the break. I know this is involved. Are there any questions on this? Okay. If there are no questions, so we can take a break until 10:05. So 13 minutes, and we will start again. Okay. Please. Let's start again. So, just before the break, we saw double selection. Essentially, what we have seen is lasso itself is not asymptotically normal. That's because of this omitted variable bias, that it's forgetting variables which are not very correlated with yi, but very correlated with di, and they create a lot of omitted variable bias. To solve that, you can use this double selection, where you run two lasso regression, one to select variables very correlated with di, and another one to select regression very correlated with variable, not regression. And when you take the union of variables selected at these two steps, then you have all the variables that can create substantial omitted variable bias. That's what's happening here. Let us now apply this double selection to this problem of estimating the gender wage gap. So we are going to take this CPS 2012 data. It's the American current population survey. Y is going to be the logarithm of wage. D is going to be a dummy variable for being female. And X are going to be all these variables. If you are widowed, divorced, separated, never married, if you have education of, I think this is more than 8 years, different types of degrees, if you live in the Midwest, for instance, and these are like experience to the square, experience to the power tree, and we are going to take all the squares on interaction of these variables. That's what this command is doing. We saw a little bit how to generate this in the first lab session, and then you can run the function from the HDM package. We will discuss it later, which is called the R-lasso effect, and these functions gives you the double selection. So we have around 30,000 observations on 120 controls. You remember that if you a way to have an idea if the number of controls is justifying high dimensionality, you should compare the order of magnitude of the square root of n to the number of controls, p. And here they are around the same order of magnitude. This is the result that we get. So we get this estimate, minus 0.28. So essentially that means that once you control for all these variables, the method finds that women earn around 30% less than men. So in the same occupation, coming from the same type of places with the same experience. This is huge. This is data from 2012. If you run that with more recent data, the difference is going down. And this is the standard error, and this is the p-value of the test. So as I said, the double selection estimator is asymptotically normal, so you can do a test with a p-value exactly the same way as OLS once you have asymptotic normality, and this is the p-value. So the p-value is 2 times 10 to the power minus 16, so it's extremely small. So you reject overwhelmingly the null hypothesis of no effect of gender. So this is like a nice application of this. You really want to put, in this problem, you really want to put as many observable control as you can to really kind of isolate the effect of discrimination. But to do that, you really need this lasso machinery, because if you run OLS, you run into troubles with an high-dimensional dataset. Okay, so we saw a first way to do inference with a lasso, and that's double selection. The nice thing with double selection is it's very intuitive. You can understand it in terms of omitted variable bias. You can think of it as essentially selecting all variables that could give substantial omitted variable bias. Now we are going to learn a second technique, which has a lot of similarities, called double machine learning. It's a bit less intuitive, but the reason why we learn about this technique is because it's very much more easily extendable to other settings than linear regression. So in particular, non-linear problems, non-parametric problems that we will see in the next part of the course. While double selection is not really extendable to non-linear models. Double machine learning is, but not double selection. So that's why we learn about machine learning, the double machine learning here, even though it is less intuitive than double selection. So, what is double machine learning? So recall that this is the model I'm assuming. Y is equal to alpha di plus xi prime beta plus epsilon I. And what we are going to do is that we are going to write the linear regression model of di on xi. You can always write such a model, you remember, where gamma is the best fitting line between di and xi. That's what we saw for OLS in the chapter 2. You can always write a linear model between di and xi, so let's write this linear model. This is not a causal model, this is just a predictive model. The only causal model we maintain if we want to interpret alpha as a causal effect is this one, the first one. So I'm going to write this model. Now I can also write a linear regression model of yi on xi. That's this one. By the way, the third model is implied by the second model and the first model, right? Because if I plug in the second model in the first model, then I have this. So here I'm just taking the first model and replacing di by its value in the second model. And so if I rewrite things again, I get xi transpose alpha gamma plus beta plus alpha ui plus epsilon I. Here I've just developed. So this gives me actually the third model where this is my delta and this is my EI. Okay, is that clear for everyone? If from the first and the second model you can get to the third model. Yes. Is there a reason why the transpose is put on? This is the same. It's actually like there is no particular reason. That's just so. Xi, what you should know is that xi transpose beta, this is a scalar, this is a real number, so the transpose on itself is itself, so it's also equal to that. So sometimes I write delta transpose xi, sometimes xi transpose delta, that means the same. Okay? Is there something that you can't read? Let me know. Okay. So how can we interpret these different things? Ui, in a way, is a part of di that is not linearly explained by xi, right? Ei is a part of yi that is not linearly explained by xi. And you have this fundamental theorem in linear regression that is called the Frisch-Volövel theorem that tells you that alpha is actually the coefficient of the linear regression of EI on UI. Alpha is actually the coefficient of the best fitting line to predict EI from UI. In other words, you should think of, you can show that alpha, which is the linear regression coefficient in this regression, is just the regression of the part of yi that is not linearly explained by x on the part of xi that is of di, sorry, that is not linearly explained by x. In a sense, here in this regression, the interpretation of alpha is that the effect of di on the part of x not linearly explained by in this regression, alpha is the effect of di on the part of y not linearly explained by x. And what the Frisch-Wohloval theorem tells you is that alpha is also the effect of ui that is a part of d not linearly explained by x on ei, which is the part of y not linearly explained by x. So that's really just a geometric result, actually. Okay, so this suggests a natural approach. In an ideal world, I would just like to regress EI on UI and then by OLS, and then I get an estimator of alpha. Of course, I don't observe EI on UI. So the first thing I need to do is to estimate them. And how can I estimate them? Well, I can run the lasso regression of yi on xi. I get the lasso estimator delta L. And if I take the residual of this lasso regression, this is an estimator of EI. Okay? This regression, like this regression model, it's a high-dimensional model because xi is high-dimensional, but I can estimate the delta by lasso and then just take the residual of this lasso regression. And that's an estimator of EI. I can also estimate UI by the residual of the regression of DI on XI. I run a lasso and I estimate this residual. And then I have two residuals, EI estimated residual, EI hat and UI hat, and I just estimate alpha by alpha hat, which is a linear regression to the OLS of EI hat on the UI hat. So this is asymptotically normal. Why? That's where the intuition is really hard to give. The formal proof is very complicated of why this is asymptotically normal, but I will try my best to give you some intuition. I don't think the intuition is as simple as for double selection, but I will try to give it to you. So the last step, it's an OLS estimator, right? And if EI hat and UI hat were equal to EI on UI, then we know that this OLS estimator will be asymptotically normal. Okay? The issue here is, of course, EI hat is different from EI, and UI hat is different from UI. However, what's interesting is that, okay, you make some estimation error in estimating EI on UI, but these estimation errors, they are both small and somehow very little correlated with each other. So what happens is the following. This is where I can try to give a little bit of intuition mathematically, but this is only a mathematical intuition. So this is my alpha hat. Okay, that's the regression, that's the OLS estimator of EI hat on UI hat. This is my alpha hat. Now I know that the OLS estimator of EI on UI has this formula. And I know that this one is asymptotically normal. So in a sense, if I want to show that my alpha hat is asymptotically normal, I just need to bond the difference between my alpha hat and alpha at OLS. And what you can see is that this is my alpha hat. The last term here is something very close to alpha at OLS. The only difference is that in the denominator you have UI at instead of UI, but let's forget about this. What you see is that if you look at the difference between alpha at and this last term here, which is almost alpha at OLS, you have all these terms. To obtain these terms, you just take the alpha at here, and you just do a trick, which is I do EI at minus EI plus EI, UI at minus UI plus UI, and then I develop this. And if I develop these terms, I get exactly the last line. And what you see essentially is that the difference between alpha hat and the last term, which is almost OLS, is always either the product of two estimation errors, that's this term, or the product of an estimation error and an error term. So it's always the product of two terms which are small in a way. An error term is something small, an estimation error is something small. For post-lasso, you could do the same kind of machinery, but what you will see is that essentially you will not get the product of two estimation error or the product of an estimation error on an error term. You will just get one estimation error. Here we have the product of two estimation error, and that's why the bias of double ML converges to zero much more quickly than lasso or post-lasso. That's because by this construction, we obtain something that mathematically gives you this product of two estimation errors that go to zero much more quickly than just one estimation error. And just one estimation error will be what lasso gives you. The double ML has this more advanced construction that gives you this product of estimation error or this product of an estimation error and an error term. Yes?
The last thing that looks like the OLS, is there a reason why it does not matter that much that in the
yeah, so it's a bit complex, but essentially, how can I explain it in the best way without being too technical? So, what determines the asymptotic normality of the OLS estimator is just that you apply. So this is going to be a technical explanation, but I don't have anything better. You apply the central limit theorem to this. So this converges to a normal zero something. Okay. Now to complete the asymptotic normality of OLS, you also need that this converges to the expectation of UI square, and this you can obtain easily by the law of large numbers. Now you have, in a very similar manner, you can show that this thing also converges to the expectation of UI square, just because UI at is just a consistent estimator of UI. And so essentially, you can show that by combining this result, this central limit theorem on the term EI UI, and this result on the denominator, you can directly show that this has exactly the same asymptotic distribution as OLS. But again, feel free to disregard this explanation. This is technical and that's not needed at all for the exam, but it's just for the people who want to go further on the math, let's say. Is there any other question on this double ML construction? Yes. Exactly. Yeah. And then you just combine both together, which has similarity with double selection, right? Because double selection you select the variable in X that have an effect on Y, and you select the variable in X that have an effect on D, and you use that. Here it's more you remove the effect of X on Y, and you remove the effect of X on D, and then you take what is left. Yes. That's very close. So this Frijvaux-Lovell theorem, this explained that's what explained that if you run a regression with fixed effect and you just estimate this regression by OLS, like with dummies for the fixed effect, it's the same as doing this within transformation, and that comes from the Frijvaux-Lovell theorem. So that's very similar indeed. Yeah. Okay. So essentially, what you can show is asymptotic normality, as I said. So you can show that square root of an alpha hat minus alpha converge in distribution to a normal 0 sigma square, where this is sigma square. Sigma square is the expectation of EI minus alpha UI square divided by the expectation of UI square to the square. To estimate it, you can replace the expectations. So the expectation will be average over all the Bayesian population. You can replace it by an average over your sample. So that's what we do here. And you don't observe EI nor alpha nor UI, but you can all replace them by the estimators. And then this gives you an estimator of the asymptotic distribution, which is a normal 0 sigma hat square, and you can use that to do hypothesis testing or confidence intervals, and these are the confidence intervals. And if you want to reject the test at the 5% level, it's when the p-value is lower than 5%. And in other words, that means alpha hat divided by sigma hat is larger than the 0.1975 quantile of the normal distribution. So this works exactly like. So the main point is to do inference afterwards, you can just apply the same routine as doing testing or confidence interval with a normal OLS to the last step regression, and that works. There is nothing to change anymore. Because of this construction, you can work as if in the last step regression it's not EI hat and UI hat that you add, but the true ones, and you can apply the standard OLS. And that's the same for double selection. You just run the standard errors of OLS to the last step regression. So if you want to do double ML with Lasso, you can you also can use this R package HDM that we will see that you will see in 2 weeks at the next session, and then you use the same function R lasso effect as for double selection, but you have to specify this optional parameter, which is method is equal to partialing out. And when you put method is equal to partialing out, that gives you double ML instead of double selection. Okay, and now we run it again on I run it again on this current population survey to estimate the gender wage gap, and I almost get the same result. As I told you, they tend to give, when n is large, they tend to give exactly the same result or almost exactly the same result. So there is no reason to really prefer one over the other. They just have different intuitions, let's say. And here you see almost the same result. The p-value is very similar, and that's what we would expect here. So is there any question on this so far? On these two methods? So make sure you understand well the intuition behind double selection. For double ML, it's much harder to understand the intuition, and I'm not sure there is a good intuition apart that mathematically it works. So just try to memorize more the construction in that case. Okay. So now we are going to move to instrumental variable models and see how to use lasso in that case. So first I will give you a reminder or an introduction to instrumental variables, and then we will see how to adapt double selection and double lasso to this case. We will not be able to finish this today, but I will start a little bit. So we said in a regression you want to add controls to make it more likely that the linear regression model is a causal model. But it could also be that if you put many controls, the exogeneity assumption still doesn't hold. That there is still something in the error term, even after you put all these controls, that is correlated with your treatment variable of interest, your DI in that case. So let me give you an example. If you have this regression, so you want to know what is the causal effect of education on earnings, you have yi regressed on di plus some xi. Here could be experience, di is education, and epsilon I is ability. I could try to put as many variables as I want in X. I will never fully be able to measure completely ability. Right? Ability is a very complex thing. I will never be able to measure it fully. So I could still believe that even if I put a lot of variables in X, my epsilon I will still be correlated a little bit with my education. If that happens, we say DI is endogenous. And in that example, that just means even for a fixed level of experience, worker with higher intrinsic ability may be more educated. One way to solve this issue, so one way to say, okay, I've tried to make to put as many controls as I can, to use lasso for estimation, but I still don't believe it's enough to think that the exogeneity assumption holds, is to use an instrumental variable. An instrumental variable allows you to do something that just static controls does not allow you to do. And an instrumental variable, it's a variable that satisfies three conditions, which are exogeneity, relevance, and exclusion. So I'll try to give you a standard example, and then we will come back to it. So suppose this is my model. I have earnings as yi, di as education, xi as experience, and epsilon I is ability. If I run OLS on this linear model, what is OLS essentially doing? It's fixing the level of experience. So it's taking people that have the same level of experience, and then among these people, looking at people with high or low education and comparing their salaries. This works if the people for a fixed level of experience who have high or low education have similar level of abilities. Then if that is the case, then what this estimates is a causal effect of education. But now if education, even once you fix experience, is correlated with ability, then what this will estimate is a mix of the effect of ability and experience. One solution to that is to use an instrumental variable, and an example of an instrumental variable in this case is college proximity at age 14. So this is a very largely used instrumental variable in this example. So what means college proximity at age 14? That means if you, when you were 14, if you grew up close or not to a college. And why is this an instrumental variable? So, and what is the idea of this? Essentially, if you take two people, you fix their level of experience. One of these person grew up close to a college, and another one did not grow up close to a college. You could imagine that on average, these two people are the same, except for the fact that one grew up close to a college and the other one did not. Now what will happen? If once you have fixed the level of experience, you compare the group of people who grew up close to a college to the group of people who did not grow up close to a college, you might expect that the one who grew up close to a college are much more likely to go to college, everything else equal, than the people who did not grow up close to a college. Because if you grow up close to a college, you can stay at home with your parents while going to college. That's much less expensive, so you're much more likely to go to college. So the idea of the instrumental variable is as follows. I'm going to fix experience. Once I fix experience, I will compare people who grew up close to a college and people who grew up far away from a college. In these two groups, I'm going to have different wages and different education. So let's say the difference in wages is $10,000 and the difference in average education is 2 years. Then I'm going to say my interpretation of this is the causal effect of 1 more year of education is 10,000 divided by 2, so it's $5,000 on earnings. And this works under several conditions, which are this really estimates a causal effect under several conditions, which are these 3 conditions. The first one is exogeneity. This college proximity cannot be correlated with the error term. So it cannot be correlated with ability. If it were correlated with ability, then again, this constriction would measure a mix of the effect of education, but also the effect of ability, right? Because people who grew up close to a college would earn more, not only because they are more educated, but because they have more ability, for instance, or less ability. So that's the first condition you need to satisfy. The second one is relevant. It's correlated with the treatment. In that case, that means growing up to close to a college, everything else equals makes you more likely to go to college, right? Because the issue that I have is if people who grew up close to a college and people who did not grow up close to a college at the same level of education, then this does not allow me to estimate any effect of education, right? By comparing these two groups, I don't have a difference in education, so that doesn't help. So that's why you need relevance. And the third one is exclusion, meaning you only cause the outcome, so wages, through the treatment. So that means college proximity causes you to have better wage only through the fact that you are more likely to go to college. It's not that because you grew up close to a college, there are more companies, so you're more likely to have a good network and these kind of things. It's only that. And why is it crucial that it's only through education? Because otherwise, when you compare people who grow up close to a college and people who grow up far away from a college, you would mix up the effect of education and the effect of growing close to a college, if this could have an effect. So what I encourage you to do, I know this is like complex from a conceptual perspective, so I encourage you to think about this example again at home and to understand exactly why each of these 3 conditions are needed to really be able to identify a causal effect with these IVs. Yeah. Sorry, can you repeat?
If there are causal effects of place of location, does the instrument
Well, that's a bit complex in that case, exactly, because you could say the fact that you grow up close to a college helps you in other way than the fact that you're more likely to go to college. Because close to colleges, there are better companies, so maybe you have friends who have parents that are CEOs of companies that they can hire you, give you a better salary, and this kind of thing. So this is linked to the location, and then in that case, there will be a failure of the exclusion, for instance. So the thing with these instrumental variables is that they are very rarely perfect. The question is more, are you able to make a critical case for each assumption? Are you able to make arguments in favor and against each of these assumptions or not? Okay, and you gave just a very good example of why we could think that exclusion fails in this example. And for any variable, you can somehow find limitations, let's say. And that's the way it is. And you will see that in the lab session and also most likely in the exam, often there is an instrumental variable. And one question I ask is, try to interpret this assumption in the context, in the economic context of these variables. Try to understand what exclusion means in that case, what exogeneity means, what relevance means, and to argue if you think it is likely or not. There is no good answer to that. Like you can argue against, you can argue in favor, you can tell me I don't know, but I just want to see that you understand the concepts and you're able to critically think about them. Okay, are these three assumptions somewhat clear? Yes.
Also, in the potential outcomes framework, the exogeneity, is it called independence? Is that possible?
Yeah, it's called independence. Yeah, it's similar to exactly. But we will discuss it. We will go to the potential. Like it's in part 3. Okay, so these are the main things you should know. Okay, so now it's already 40. So what I will do now is just summarize what we did today, and we will finish next week on instrumental variables. So let's just summarize quickly what we did. So first, we discussed inference with OLS. So you remember inference is essentially doing hypothesis testing. And we discussed how to do hypothesis testing with OLS. So to fix ideas, I gave one example is we want to know what is the causal effect of education on earnings. So we postulate that this is a true causal model. Again, that may not be realistic, but we postulate that for now. If this is a true beta causal model, then if we observed all the Belgian population, then we could just run OLS to estimate this model on all the Belgian population. We would get beta 1, and my beta 1 would be just the causal effect of education. Now, in practice, I don't observe the full Belgian population. I observe, say, a sample of 1,000 Belgian, and I run OLS on this sample, and I get an estimator of beta 1. And the question is, can I confidently conclude from this estimator that beta 1 is different from 0? So that's the example you have here. So for instance, if I get beta 1 hat is equal to 0.2, it's very hard to know if that means the true beta 1 is different from 0 or not. To know that, you need to somehow have an idea of what of the statistical uncertainty of the problem. So this is the hypothesis testing formalism that we have with OLS. So first, so we want to test the following hypothesis. So we want to test H0 beta 1 is equal to 0. We want to know if there is or not a causal effect of education. Versus H1 beta 1 different from 0. How do we proceed? As I said, we do that in a manner which is very similar to the justice system. We start from the assumption of innocence, or in other words, in the statistical context, from H0. Under the assumption of innocence, there is a kind of distribution of likely observations, of likely facts I should observe. Under the assumption of innocence, it's overwhelmingly likely that I observe the suspect at work or at home at the time of the murder. It's extremely unlikely that I observe them close to the murder place. Of course, if I do that, that doesn't mean for sure that they are the murderer, but that means it's very unlikely that they were not the murderer, because if they were not the murderer, it would be very unlikely that I observe them close to the murder place. In this way, for the statistical problem, I do something similar. Under H0, I can mathematically determine what is the distribution of beta hat I should observe. The distribution of beta hat is actually the distribution of all the possible beta hats across all possible samples of 1,000 Belgians. I only have one of these samples, but if in my one sample I find something that is very unlikely under this distribution, then probably the premise of this distribution, which is H0, is false. And that's how we work. So we start from this asymptotic distribution. This is the asymptotic distribution. So I know that this is the distribution of beta hat I should observe. If the null hypothesis was correct, if beta was equal to 0, I should observe a normal distribution like that, centered in 0. If the beta hat in my sample is on the tail of this normal, then it's very unlikely to happen if H0 was true, so I can reject H0. If the beta hat in my sample is in the middle here, then it's very likely to happen under H0, so I have no evidence that tells me that H0 is false, I don't reject it. So this is also an example with the graphs, but we will not go through it again. So this is the main idea for OLS. Now the issue with the lasso, when we move to high-dimensional data, is the fact that this asymptotic normality of OLS that allows us to build up this test, this hypothesis testing, doesn't hold for the lasso. And that's the main difficulty. So we need to adapt the construction to obtain new estimators that use lasso at some step, but which have this asymptotic normality that I can use to do this inference. And we saw that, so the main issue for the lasso is that this L1 penalty, so what we call the L1 penalty is a regularization term of the lasso that we introduce with respect to OLS, creates bias, which makes that the asymptotic normality doesn't hold anymore. And there are two methods to solve this. They are double selection and double ML, double machine learning. And as I said, they are both asymptotically equivalent. So the formalism is as follows. This is the model. So I have yi is equal to alpha di plus xi transpose beta plus epsilon I. I assume exogeneity, linearity. So here I want to estimate alpha. I assume that this is the causal effect, and this is the causal model. The main difficulty is just estimating alpha. Xi is high-dimensional in that case, so OLS will not work. We saw that in the previous chapter, so I have to use something like lasso. And I want to test H naught, alpha is equal to 0, versus alpha different from 0. Another example is a gender wage gap that we saw. So I want to isolate the effect of gender discrimination on wages. So I want to regress the logarithm of wage on a dummy variable for gender and many controls. A naive approach to this will be to say, I do post-lasso. So post-lasso is this. I first run a lasso regression where you will notice, as I said, I don't penalize alpha because I always want to keep alpha in my regression, right? Because that's my parameter of interest. And then lasso gives me an estimator of beta. In practice, lasso gives you a lot of 0 in this estimator of beta. So I just take the variables which are of non-zero coefficient, and I say these are my selected variable. And then in the last step, I just run the OLS regression of yi on di on the variable selected by the lasso. And you could tell me, yes, the last step is an OLS regression, so this should be asymptotically normal. I don't have a problem, right? I can run this OLS regression because lasso selects only a few variables, so the problem in the last step is low dimensional. And you could tell me it's OLS, it should work. But actually, in practice, it doesn't. And why doesn't it work? That was this omitted variable bias. So omitting a variable in the model only creates bias if two conditions are met. This variable has an effect on y and is correlated with di. What happens here? When you run this first lasso regression, you're going to omit the variables which are not very correlated with yi, so which have a very small b, but very correlated with di. And these variables can still create substantial enough omitted variable bias to make asymptotic normality fail as a last step. And that's what this slide says. To solve the problem, we will run two lasso regressions. The first lasso regression is that of di on xi, and the goal of this lasso regression is to select the variables which are very correlated with di. The second lasso regression is that of yi on xi, and then we select the variables which are very correlated with yi. And then we take the union of the two selected set of variables, we put them in the last OLS regression now. And the only thing essentially that these two steps can miss are variables which are at the same time not very correlated with di and not very correlated with yi, right? Because if a variable is very correlated with di, I'm going to pick it up at the first step. If it's very correlated with yi, I'm going to pick it up at the second step. So the only variables that I might miss now are variables which are at the same time not very correlated with di and not very correlated with yi. But these variables, they create almost no omitted variable bias. So essentially, the fact that I might miss them is not a problem, and asymptotic normality still holds. And that's why this is a post-lasso, this is a double selection, and then the double selection works. Okay, and then we run this estimation, and we found a gender wage gap of around 30%. Then you have this other approach called double ML, and all this approach is based on the Frisch-Ball-Oval theorem. And the Frisch-Ball-Oval theorem just tells you that alpha is the best fitting line between EI and UI, where EI is a part of Y not explained by X linearly, and UI is a part of D not explained by X linearly. So that gives you a natural estimation procedure. I'm going to estimate EI on UI by lasso regressions, by the residuals of two lasso regression, and then I'm going to estimate alpha by running OLS on EI at, of EI at on UI at. And it turns out, for complex mathematical reasons, that this last OLS works, and you can do hypothesis testing normally with OLS on this last regression. Okay. So that's another way to do inference. And then we quickly discussed instrumental variables. So instrumental variables are solutions when you believe that even if you put a lot of controls in your regression, the exogeneity condition is not going to hold still. You might want to put a lot of control, but that doesn't mean it will solve all the exogeneity problem. As I said, if your epsilon I is ability, in the example on earnings on education, then I can put as many controls as I want. I can't measure perfectly ability, so I might still believe that what is left in my error term, the part of ability that is left in my error term once I've put IQ, parental education, and these kind of things, is still correlated with education, and then I still get bias. So to solve this problem, I can use an instrumental variable. And an instrumental variable, it's a variable that satisfies three conditions. The first one is it is exogenous, so not correlated with the error term. The second one is that it's relevant, and the third meaning it's correlated with education. The third one is that it's excluded, it has no direct effect except through education. The example that we had is college proximity at age 14, and the idea is as follows. The way the method works is I'm going to fix X, so here experience. I'm going to take people with the same level of experience, and I'm going to compare people with different levels of the instrumental variables. We call that an IV. People who grew up close to a college and people who don't grow up close to a college, among people with the same level of experience. Now, if the three conditions hold, the only difference between these two groups is going to be that one group has more education than the other one, because growing up close to a college makes you more likely to go to college. And then I can just compare the wages between these two groups, and the difference in wage will be the effect of this the causal effect of this difference in education. So that's why this IV allows me to somehow pin down the causal effect. In that case, yes.
Because we assume that both groups have the same average ability.
Exactly, and that's the exogeneity condition. So it's not correlated. The IV is not correlated with the error term. So college proximity is not correlated with the error term. But again, you also need the two groups to have different education, right? Because if they have the same education, you can't observe the level of education. And you also need that college proximity itself only has an effect through education. Because otherwise, when you do this comparison, what you estimate will be a mix of the effect of education and the effect of college proximity itself. One last remark, and then I'll let you go, is also that to make this exogeneity condition more likely, you may still want to put controls, right? The more you put control, the more you will still put this, you will still make this exogeneity condition more likely. So you might still want to estimate models with an IV, but also many controls. And we will discuss to do that in the next class. Okay, so thanks a lot. You can come to me if you have any question, and we see each other next week also in this room.